Welcome into last video for this topic. All right, so what have we not covered so far? Well, polar equations, but we need area for polar equations. We'll just say area for polar, and I'm just going to write across the top here so I don't run into space issues while solving these problems, because they do take quite a few steps and I don't want to skip anything. So when I'm saying area really quick, what am I referring to? I'm referring to integration, right? Okay. You know what? We'll just go for it over here. So, area, polar equations, integration. The equation that we'll need, and I'm going to add on some stuff that we should know, is going to be equal to 1/2 integrate from a to b, and these will be angles of r squared d theta. Right, so this is our equation. Right, you give me some polar equation, we find r squared, and we integrate. Right, seems easy enough, but there is something that we need to remember all the way back from trig. And so I'm going to give us one of the rules right now. It's going to be that sine squared theta is equal to 1 minus cosine of 2 theta over 2. All right, so this is a trig identity that we will need. There's a cosine one that goes with it, but I'll introduce it in the next example. All right, so let's go through this slowly. So I want to find, let's just write it up here briefly, find area enclosed by, and let's say r is equal to 3 plus 2 sine of theta. Right? Okay, so we have our r. Notice that I didn't specify an angle, so if the angle's not specified, we're going to do one full revolution from 0 to 2 pi. So let's go ahead and start writing that out. So we have that area, I'll write all the way over here, is equal to 1/2. We'll go from 0 to 2 pi of r squared. So we have 3 plus 2 sine of theta squared d theta. Right? Okay, so we have a little bit of algebra to do here because we have to square, right, 3 plus 2 sine of theta. So I'm just going to write it over here. We still have that 1/2 hanging on the outside. We still have 0 to 2 pi. I'm going to try to write so you guys can read it and I don't cover it up. And then once we go ahead and square this, we end up with 9, 3 squared, plus 12 sine of theta, plus 4 sine squared of theta, d theta. Okay, so pause for a second. Let's check out the algebra here. 3 squared, 9. This 12 sine of theta is coming from the fact that 3 times a 2 sine of theta will be 6 sine theta, and we do that twice, so that's where we get the 12 sine. And 4 sine squared theta, right, 2 sine theta squared. Now, we have it all set up, right? Maybe we're taking a look at it and we go, okay, well, I know how to integrate 9, and I know how to integrate 12 sine of theta, right? Where does a positive sine come from? A negative cosine. However, remember, this sine squared theta is not easy to deal with. So we have our trig identity that we're going to immediately do a substitution here for. Right, so I'm going to write it over here. We'll just go from left to right. This is going to be equal to 1/2 still. We still have not integrated, right? So no calculus yet, just all trig and algebra. We have our 9 plus 12 sine of theta plus 4, and now we're going to, right, substitute. I have 1 minus cosine of 2 theta over 2 1, 2, and one more, d theta. Let's try back to the yellow. Okay. Let's go ahead and we'll just do the algebra here before we go to the next step. 1/2, still 2 pi, 0, 9 plus 12 sine of theta. And what do we notice here with the 4 and the 2? Right, they will cancel out. I'll cancel them out in pink since I wrote them in pink. That's going to go away. This will go to a 2. So now I'll have plus 2 minus 2 cosine of 2 theta, d theta. Okay, so again, just the 4 and the 2 cancel out. We distribute the 2. And of course, we do have like terms here, right? This 9 and this 2 here can get added together. Right, I don't want to write a whole nother line just to add 9 and 2, so we'll just do the integration at once, but we're going to combine them. So here's 9 plus 2, and that's 11. So we're going to go for the integration here. So 1/2. Let's go ahead, we'll put a bracket. And we have 9 plus 2, which is 11, but the backward step with integration with respect to theta gives us 11 theta. And where does a positive 12 sine of theta come from? A minus 12 cosine of theta. And lastly, so this is the tricky one, right? Where does a negative cosine come from? Comes from a negative sine, right? So we have minus, yep, this is fine, minus 2 sine of 2 theta all over, right? Now we need to do something what's like a reverse chain rule, right? So this ends up being a reverse chain rule here. And so instead of thinking about a chain rule, we would multiply by the inside. Now we're going to divide by the inside. All right, so these will cancel each other out. And we need to go from 2 pi to 0. Okay. So we'll do it piece by piece. All right, so real quick, the 9 plus the 2 is the 11, backward step 11 theta, 12 sine of theta, backward step negative 12 cosine of theta. We have a negative 2 cosine of 2 theta. The backward step is going to be this sine on the outside, but we have to divide by the derivative essentially of the inside. So that's why those 2's cancel out. And finally, equals 1/2. And now we're going to have, let's plug in the 2 pi first. What do we get? We get 22 pi minus, well, what's going to happen here? Cosine of 2 pi is going to be 1. So minus 12. Awesome. And if we plug in 2 pi to sine of 2 theta, that's going to be 0. So we don't need to worry about that, right? Sine of 4 pi is 0. Minus, and now we'll plug in the 0. Well, if we plug in 0, 11 times 0 is 0. Minus cosine of 0 is going to be 1 also. So we have another minus 12 here. And sine of 0 will also be 0. So this is it. We've evaluated everything. And if we have a double negative, right, this becomes a positive. And now we can cancel out this as well. Right? So we have 1/2 times 22 pi, or in other words, 11 pi. And that is it. Right, so real quick recap. Again, this, right, I know this is from a long time ago. Right? Sine squared theta is equal to 1 minus cosine 2 theta over 2. That's from a long time ago back in trig. But we do need to know that for this class. Right? So we start with our equation. Area is equal to 1/2, 0 to 2 pi in this case. We have our radius, 3 plus 2 sine of theta squared. We have some algebra to perform here, right? By actually squaring it. We make our simplification here, once we substitute what sine squared is equal to, right? Using our trig identity, the 4 and the 2 cancel out. And now we just have to combine like terms, right? The 9 and the 2 are the only thing, the 11 theta. And as we've gone through the problem, right, backwards from sine, negative cosine, backwards from negative cosine, negative sine. The reverse chain rule is kind of the hardest part here to remember, right? So chain rule, right, we take the derivative of the inside, we multiply it. Reverse, we take that derivative and we divide it. Okay. And after that, right, we're just evaluating 2 pi and 0. And we should end up with 11 pi. So I'm going to do another one just like this. In case we got stuck at any points, I will introduce the other one, which is the cosine squared. So I will be right back with another problem. All right, let's do one more similar, right? So I'll remind us of the equation. Right, so what is it? Area is equal to 1/2 integral from a to b, right, which are angles, r squared d theta, right? So this is what we're going to need. And I'm going to introduce the other trig identity that we're going to need here. I'm trying to get away from being exactly behind this. Cosine squared of theta is going to be equal to 1 plus cosine 2 theta over 2. Right, so this is the other trig identity. We have the sine one. Here is the cosine one. And same idea, we're going to find the area enclosed by. So let me write it over here so I'm not behind. Find area enclosed by. We'll do r is equal to 2 plus 2 cosine theta. Right, again, notice that I didn't specify the angle, so we're just going to do one full revolution. Right, so we'll start all the way over here. So we'll do, this is going to be area is equal to 1/2 on the outside from 0 to 2 pi. And same idea, right? 2, ugly 2, plus 2 cosine of theta squared d theta. Right, so similar format to the previous problem, right? What are we going to do now? We have to do some algebra to extend all this out. So this is equal to the 1/2. We still have 2 pi. We still have 0. This now becomes 2 squared, 4, plus we have 2 times 2 theta, and 2 of those, so it ends up being 8 cosine theta, sorry, plus 2 cosine theta squared, which is 4 cosine squared theta d theta, right? Okay. So that is the first part. Again, similar format to our last problem. Notice when we're doing the integration. Integrating 4, no problem. Integrating 8 cosine of theta, no problem. 4 cosine squared, right? Well, what do we do with that? Luckily, we have our trig identity, right? So we're able to make that replacement. Let's go ahead and do that now. So we have equals 1/2, 2 pi, 0, 4 plus 8 cosine of theta, and then we're going to write plus 4, and then instead of cosine squared, right, we will write 1 plus cosine of 2 theta over 2. So we have this nice cancellation that we can make. Let's add one more parenthesis here, d theta. And what do we notice, right? This 2 here in this 4, right, are going to cancel each other out. Well, I mean, the 2 will cancel out. This will become a 2. Let's go ahead. We'll just keep doing some more algebra. We haven't reached the calculus yet. 1/2, 2 pi, 0. Now we have 4 plus 8 cosine of theta. You guys can still see that. I'll switch colors just in case. We'll distribute this 2, so plus 2. So maybe we notice here, right, this 2 and this 4 obviously are like terms. We're going to end up putting them together. Give me 1 second. Let's see if we can get this. There we go. And then the 2 will also distribute 2 plus 2 cosine of 2 theta d theta. Okay. Now, again, same thing as the last example. I'm not going to take a whole step to combine the 4 and the 2. We'll just assume that we can do that in one step, but I will say it out loud as we do the step here. So we're going to actually do the integration. We have the 1/2. We'll put this in a box. We have 4 plus 2, right, which is 6. The backward step, or the antiderivative of 6, with respect to theta, will be 6 theta. Plus, where does a positive 8 cosine come from? It comes from a positive 8 sine. And right here's like this reverse chain rule, right? So where does a positive cosine come from? Again, a positive sine. So we end up with plus 2 sine of 2 theta over 2, right? Divide by this inside value, right? The derivative of 2 theta, 2. And we need to evaluate from 2 pi to 0. Maybe some of us are looking at this going, oh, this is actually nice. Anybody spot why this is a nice problem? Of course, the 2's cancel out. Why is this a nice problem? Well, think about sine here, and think about these two values, 2 pi and 0. Right? What do we know about sine? Sine of 2 pi is always going to be 0. Sine of 0 is going to be 0. So this whole thing is essentially going to evaluate to 0, but we'll walk through it. Right, so we have equals 1/2. If I plug in 2 pi, I'm going to get 12 pi. Plus, and I'll even write it here just to prove a point. So this is when we plug in 2 pi. Right? Sine of 2 pi, that's going to be 0. Plus sine of 4 pi, that's a 0. Minus, now what happens when I plug in that 0 there? We get all zeros, right? 6 times 0, 0. Sine of 0, 0. Sine of 0, 0. So this is just a giant 0. And so what do we end up with is just 1/2 times the 12 pi, a bunch of zeros after that. And we just get a nice 6 pi, right, is our answer. Okay. So one more time, right? We have our equation, 1/2 integrate between a and b, 2 angles of r squared d theta. We do some algebra here, right, to extend that r squared. Then we see, right, the 4 is fine, the cosine theta is fine, but this 4 cosine squared is not fine. We don't know how to integrate that. So we end up having to use a trig identity from way back when, substitute it in. We make some algebraic simplifications, right, with this 4 and 2, right, combining them, and then we integrate. Right, integrating 6 is not that bad. Integrating the cosine theta is not that bad. We do have this awkward reverse chain rule, right? But after everything's said and done and we input the 2 pi and the 0, we end up only getting one value here with the 12 pi. All of this stuff here evaluates to 0, regardless if we plug in 2 pi or 0, right? Sine of 2 pi or 0 will also be 0. So we end up getting this nice 6 pi. As a reminder, again, so the 2 trig identities, you don't get notes for your exam, so it is helpful to know these, right, in case you run into them again. Write them down, memorize, trig identities. Okay, I'm going to do another example, and then I'll allude to what you should try for number 30, since it is a different type of integration problem. I will see you in a sec. Welcome back. There's a couple variations of the area problem thrown into your homework. There's a lot in general, but just going through the ones that are towards you guys. One of the ones that you'll see is it's going to say, let's see if I can get this to work. Find the area, I'll write this way so I'm not enclosed by 1 loop of, in case you guys are copying down, and they give us r squared. R squared is equal to, it is going to be sine of 4 theta. So find the area enclosed by 1 loop of r squared equals sine of 4 theta. Right, so we do have our area equation, so we're just going to write that down over here. All right, we know that area is equal to 1/2 from a to b of r squared. And the nice thing here is d theta. Hopefully that shows up. It should. It's because the is still, there we go. There we go. Right, so the nice thing here is they already give us the r squared, right? So that part's done. There's no need to square anything, so we don't have to deal with those ugly trig identities, which is nice. However, notice it says find the area enclosed by 1 loop, right? So it is helpful to know this graph. I'll attach a section in the book, but it's in the there's a bunch of different types of graphs that you can go through with polar equations. I think there's 8, so I'm just going to post the link to the book where you guys can see all that. I know there's a few questions on identifying graphs. Essentially, if you want to, we can just plot points, and that's what I'm going to do here, somewhat. So let's get a visual of what this looks like. Okay. Now, the reason why I want to get a visual is because we can kind of fill this out. So let's go ahead and write what we know. Put a little line here. Area is equal to 1/2. I don't know, right, what I'm bound by. That's why I'm writing this graph here. And we can write what r squared is. It's sine of 4 theta, d theta, right? And we could even do the integration, but we just need the bounds. So think about what it means by 1 loop, right? 1 loop means I start with a radius of 0, and I'm going to end with a radius of 0. Think about just making a loop in general, right? I won't make it on the graph yet. But if I start here, and I come out, at 2 points my radius was 0. When I started, and when I finished, my radius was 0, right? And so what I'm going to do here is I'm just going to take my radius, right, and set this equal to 0, right? I want to know when my radius is equal to 0. And so all I need to do is say, well, when is sine of 4 theta equal to 0? Right? And we know, and we want the first 2 attempts. So the first one is when we plug in 0, right? So at 0, at angle equals 0, right? No angle, we're 0. And also, so we'll put theta equals 0. And the very next time we equal 0 is when this is going to be sine of pi, right? So if I plug in pi over 4. So this is the tough part, and I want to make sure I don't lose people. 4 times pi over 4 gives me sine of pi. That's going to be 0. So I know, and I have this loop here, that all of this is occurring between our bounds 0 and this confused me over here. Pi over 4. That's just a squiggly, not to be confused with an integration sign. Right, so again, the tough part, this is kind of all given to us, but we need to know our bounds here, right? And so our bounds, if it says 1 loop, I need to know if I start with a radius of 0, right, which is what's happening, and when do I come back to having a radius of 0, because that will close my loop. So I took my radius, even though this is r squared, because it's 0, it doesn't matter, set it equal to 0, and of course the first one's at 0, right, 0 degrees, we're equal to 0, and the next time is at pi over 4. So we've completed a full loop after we've traveled from 0 to pi over 4, right? So that's all I need to do. So let's continue the rest of this problem now, and it shouldn't be too bad. We have the 1/2. We don't even need to do that, right? We'll just make this a bracket here, because I can immediately integrate, right? Where does a sine come from? It comes from a negative cosine, right? That's a positive sign. So negative cosine of 4 theta. And remember, this is this reverse chain rule type where I also have to divide by 4. And I'll use a different color here. we'll make a real bracket here, between pi over 4 and 0. All right, so knowing the radius squared, not difficult. There's no trig identities, that's given to us. We have our equation. We should have that down hopefully by now. And we just need to find the bounds. So when I go to plug in everything, let's see what happens. I have 1/2, and I'm just going to pull this -1/4 out, right? There's a negative sign there, there's a 4 there. So let's pull the -1/4 out. And now I can actually just evaluate the cosine of 4 theta. Right, so cosine of 4 times pi over 4, so we end up with cosine of pi. Right, that's what happens if I plug in the pi over 4, 4 times pi over 4, pi, minus cosine of 0. Right, so we have -1/8 hanging out on the outside. And now we have cosine of pi, which is -1, minus cosine of 0. This is just supposed to be a 0. Sorry, that looks like a theta. Minus 1. Right, so -1/8 times -2. We're going to get a positive 1/4. Right, so that is our final answer there for the area enclosed by one loop. We should all have a very similar type of problem for, I'm not sure what number this is, but I would imagine this value is going to change for some of us. So notice the relationship here. If I drew this all the way out, this 4 tells me that I have 4 loops. Right, I end up with 4 loops. Okay, so I will leave this one here. If any questions, again, feel free to ask. I'm going to give a hint on number 30. So a short video after this is a hint on how to start 30. Okay, last quick video for this one. Just giving a quick hint, this is problem number 30 in the homework. Number 30, okay? And so we want to find, I'm going to let you guys read the wording. So it's number 30, right? We want to find the area enclosed by these 2 polar equations. And we have 2 of them, so it's going to be r is equal to 3 sine of theta. And the other one will have r is equal to 3 cosine of theta. And it gives you a graph with it as well. Right, so number 30, it's asking for the area enclosed. And so I'll do a quick depiction of the graph really quick. It looks something as such, something like this, and then we'll draw, my graph won't be great, but you'll get the idea. Right, so we have these 2 overlapping circles, and the area that you're asked to find here is this area here. And so the first thing that you want to do, and I'm going to help you out with this, is identify which circle is which one goes with sine, which one goes with cosine. Right, so the very first thing you can do is, well, let's plug in an actual value, right? So let's say we plug in 0. What happens? Sine of 0 is going to be 0. So if we look here, right, this specific point, which is the upward circle, goes with sine. So this is 3 sine, and maybe you're still not convinced here. Right, well, let's plug it in the other. If I plug in 0, I get 3. Right, which is this value here. At 0, I get 3, radius of 3. So this one, right, this sideways circle is the 3 cosine. Right, so we can immediately tell which circle is which. That's step number 1. Sorry. Step number 2 is to go, okay, well, it might help also to know where they intersect. Right, this is going to be a helpful thing. Where do they intersect? What is this specific value? And also, right, if it intersects there, how can I split this up? Right, because this is right down the center here. If I drew a line. So what I will tell you is you want to break this up into 2 separate integrals. So I'm going to give away quite a bit of the problem here. 2 separate area integrals, right? So I have 1/2 right? This is area. And I know there's some values or some angle that I'm going to need to integrate between for this bottom half, right? So I'm going to find half of the area in one of them and half in the other, right? So I'll need 3. Now it's deciding not to work. Let's try the yellow. I'll need 3 cosine of theta squared d theta. And that's going to get me this bottom half here, right? I don't want to overlap with the yellow, but you can imagine this bottom half. Plus, right, I still need to go get the other part, 1/2, and I'll need, again, right, 2 bounds for 3 sine of theta squared d theta. And this one will get me the top half, right? So we're adding these 2 things together. So it's 2 separate parts. So I've kind of done the whole problem for you. All you need to do, right, is 2 things, right? First, find the bounds for each one of these. Secondly, what are we going to notice here when we do this squared? We'll end up with 9 cosine squared. So remember, what do we know about cosine squared in our trig identities? Look back in the past examples. Same thing here, 9 sine squared, right? We don't know how to do an integration of sine squared, but we do have our trig identity that I introduced in the first example. So go back through that. Hopefully this quick hint helped, right? Again, just the bounds and of course the integration, and you should be good. All right, come to class with questions, more videos to come. Thanks, guys.